Thanks for watching this video. In this video, I will talk about our work, Target Relevant Knowledge Preservation for Multi-Source Domain Adaptive Object Detection. In the past decade, convolutional neural networks have achieved great progress and delivered significant improvement in visual object detection. Unfortunately, the well-built detectors suffer from remarkable performance drop when applied to unseen scenes due to domain shift. Since it is rather expensive and time-consuming to annotate newly collected data, Domain Adaptive Object Detection (DAOD), which aims to adapt the detectors trained on labeled source domain to the unlabeled target domain without extra annotations, has been receiving increasing attention. Many efforts have been made on DAOD in the literature, and the methods mainly address it in the paradigm of adversarial feature alignment or semi-supervised learning. The former directly aligns the features in the source and target domains. The latter predicts pseudo-labels according to the model trained in the source domain and adopts them as guidance to the target domain. Multi-source domain adaptation, or MSDA for short, is considered as a more practical scenario in unsupervised domain adaptation, since it assumes that various sources are available for better adaptation to the target domain. To the best of our knowledge, the only attempt is recently given by DMSN. However, there exist two major limitations. Firstly, the divide and merge spindle network conducts early alignment of multiple sources by simple combination or multi-source alignment, which often incurs degradation of domain knowledge learned in individual sources. Motived by this, we propose an adversarial multi-source disentanglement method, or AMSD for short, to preserve source domain-specific knowledge and simultaneously perform cross-domain alignment. Secondly, the loss memory bank measures target-relevant knowledge in source domains by a temporary discrepancy, leading to a local optimum. Motived by this, we develop a holistic target-relevant mining scheme, or HTRM for short, to reweight the source images according to the source target relevance. As consequence, we propose a novel target-relevant knowledge preservation (TRKP) approach to multi-source DAOD. As shown in this figure, TRKP performs multi-source DAOD in the teacher-student framework, where a multi-head teacher network is constructed to extract knowledge from individual labeled source domains and mentor the student network on detector building in the unlabeled target domain. To restrain knowledge degradation, the teacher network embeds the AMSD module to preserve source domain-specific knowledge acquired by corresponding independent detection heads as much as possible during cross-domain alignment. Further, the HTRM scheme is developed to reweight source images according to source target relevance. By this means, the teacher network is enforced to capture and highlight target-relevant knowledge at the global level, thus benefiting domain gap decreasing for detector adaptation in the target domain. As for the AMSD module, as displayed, the teacher detector utilizes a multi-head structure, which has multiple ORI detection heads, one per each individual source domain, with a shared backbone and RPN. In order to diminish the multi-source correlations, the teacher detector adopts a gradient reverse layer and is trained by minimizing the detections loss formulated in this equation. After training, the teacher detector is utilized to perform multi-source knowledge adaptation. Concretely, pseudo-labels are generated for unlabeled images in the target domain by using the teacher detector, which are subsequently used to supervise the student detector in the target domain by optimizing the detection loss. Due to the lack of guidance of the target, images that are less relevant to the target domain are given the same importance as more relevant ones, which deteriorates the quality of knowledge adaptation. HTRM can encode target-relevant knowledge at the global level. As summarized in the algorithm 1, HTRM firstly computes its frequency that locates in the k-nearest neighbors of an image from the target domain, and then calculate the importance of each source image. The reweighted importance of images from multiple sources are then adopted to train a target-relevant teacher detector by minimizing this loss. To evaluate the performance of the proposed method, we conduct experiments under three different settings. The first one is cross-camera adaptation. We use the Cityscapes and Kitty datasets as the source domains and the BD100K as the target domain. This setting focuses on the domain shift caused by various settings of camera parameters, viewpoints, and scenes. The results clearly shows that our method improves the accuracy by a large margin. The second setting is cross-time adaptation. We use the daytime and night subsets in BDD100K as the source domains, and the dawn/dusk subset as the target domain. This setting focuses on the domain shift caused by changes in illumination and scene in different time. As displayed, the proposed TRKP improves the performance by large margins. It is worth noting that TRKP exceeds Oracle significantly. The last setting is mixed domain adaptation. We use Cityscapes, Skoko and Synscapes as the source domains and the BDD100K as the target domain. This setting has multiple domain shifts. Despite of more challenges, TRKP still achieves a significant performance gain, demonstrating its effectiveness when applying to mixed source domains. We also conduct ablation studies on the effect of multi-source disentanglement and the influence of hyperparameters on the performance of the proposed AMSD and HTRM. In addition, to display the effectiveness of the proposed HTRM scheme, we additionally demonstrate the images with different target relevance weights. As shown in this figure, the source image with a larger weight clearly has a more similar appearance to those from the target, in regard of the illumination condition. Please contact us if you have any questions or ideas. Thanks for watching.